In this first video, we're going to look at the graphs, connecting the graphs. In these three videos, this first video, we're going to look specifically at finding extrema, local extrema, what it looks like graphically, do an example using the first derivative test, and also look at a lot of definitions of what it looks like graphically. So there's a lot of stuff that you'll need to be writing down. Might need to pause the video a lot. I'm going to go kind of fast on this. So first of all, looking at this graphic on the first page of our notes, you have, first of all, let's look at this point. What we know, this is the local maximum. We find the maximum point at horizontal tangents. Remember, horizontal tangents are where, like it shows you here, the first derivative is equal to 0. So when we're going through and finding local extrema, we know to go through and find all of your horizontal tangents. These two are pretty obvious because this first one is the local maximum, where it's the highest point locally. This is the local minimum, okay, where it's the lowest point locally here, or relative. That's another one. Another term that's used is a relative max, a relative min, same thing. So this is, you notice here, this is a critical point because remember, critical points occur also where the first derivative is equal to 0, and this is a cusp. And so we have to look at cusps and also endpoints as critical points as well, because something weird with the graph is going on and we have to test to see really what's going on. And then also you notice when we find horizontal tangents, you get this answer here and this answer here as horizontal tangents, but there's nothing going on. So don't just assume that when you find horizontal tangents or critical points that there are extreme values, because on the left side of this critical point, you notice all of the slopes are positive. And the definition of a extrema is that the slopes change from one side of that critical point to the other. And you notice from one side of the critical point, they're positive, and on the other side, they're positive. So they don't change. Unlike this one, where on one side they're positive, the other side they're negative, and on one side of this one it's negative, on the other side it's positive, and so forth. Okay, so those are local max min. So don't always assume when you find a critical point that it must be a local max or min, because that's not going to be the case. Then there's this other thing called absolute max and min. So absolute max and min, you have to again look at all critical points. That includes horizontal tangents where the slope is equal to 0. That includes cusps, corners. When you're looking at a piecewise function, that's where they come together. You have to test that point. And then also you have to test endpoints to determine local max and local mins. And I've talked about this in other videos, and it's definitely just as important here as it was in all of the other ones. So this is why it's critical that you, test those critical points, pun intended, using what we're going to learn as the first derivative test. So before we go there, let's look at all these graphs and different points and what they could look like at all of those points for max, mins, all of that stuff. Okay, so let's take a look at this, what this looks like. I have all of these, so go ahead and pause the video as you need to sketch these graphs. So first of all, we're looking at a graph. You have all of these critical points. All of these are going to be the same. They all have a critical point at this value C. Okay, at this critical point, something occurs. We don't know what, but graphically we can look. On the left side of this C value, you notice all of your slopes are positive. And then on the right side, you notice all of your slopes are negative. That indicates what we know as a local maximum. When the slopes go to positive to negative, that's a local maximum. And again, it doesn't have to occur necessarily at a horizontal tangent. So not all critical points occur at horizontal tangent. You know, this one is not a horizontal tangent because the slope is not 0 there, but however, it's still a local max. So you have to be careful. Local minimums look like this. On the left side of your critical point, all of your slopes are negative. On the right side of your critical point, all of your slopes are positive. And so then that would be a local minimum. Same thing here. Again, this is a corner, so it does not have to be a horizontal tangent at all. And then now, looking at the third option, is what if it's always positive or always negative, but you still have your critical points. either at a corner, cusp, or horizontal tangent, or an endpoint, which we'll look at next. So you still got stuff going on, but if you use the test and look at your values of the derivative, you notice on both sides, in this case, it's all positive, meaning no extrema. And on both sides here, it's negative, indicating, again, no extrema. So there has to be that sign change. Your derivative has to go to positive, negative, or negative, positive in order for there to be a local extrema. And again, this is only local extrema, not necessarily max, mins, whatever. But this is for local extrema. So then, looking at endpoints, looking at your left endpoints, if you have a left endpoint and then to the right of that left endpoint your slopes are negative, that indicates a maximum, local maximum. And you have your left endpoint, which is a critical point, and to the right of that your slopes are positive, that indicates a local minimum. So that's for left endpoints. So for a right endpoint, if you look just to the left of that and you notice all of your slopes are negative, then that means that it's a local minimum. At a right endpoint, you look just to the left, slopes are positive, getting bigger, bigger, bigger up to that point. That indicates a local maximum. Okay, let's take a look at this example. So first of all, it says use the graph below to estimate where the graph is increasing, decreasing, and to identify all local extremas. So first of all, let's look at it where it's increasing. Okay, so where it's increasing, we'll do this in all red. That means the first derivative is greater than 0. That means the slopes are positive. That means the graph is going up. Okay? You look at your critical points. I have a critical point here, 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 and here. And the only place where your slopes are positive are between here, because all these slopes are positive. So where it's increasing, so we would say that it's increasing on the domain from from negative 1 to positive 1. It's increasing on that domain. And then where it's decreasing, you notice from this point through here, all of your slopes are negative. So that indicates it's decreasing. So where it's decreasing, your slopes are less than 0, or your first derivative is less than 0. Your slopes are negative. And your graph is going down. And then again here on this interval also. So we're going to say that the slopes are negative. On the intervals, we'll say from negative 2.5. We'll assume that it ends. We'll assume there's no arrows there, so we'll assume that it ends right there. So we'll say from negative 2.5 to negative 1, unioned with from, let's see, what was it, 1 to 2.5. Okay? Now we're going to go one step further and look at all of our local, and then I'm going to throw absolute extrema in there. So first of all, let's identify our local extrema. Right here, it goes from negative to positive, so that is our local minimum. And then this, since it goes from positive to negative, is our local maximum. Then also, these are local max and mins, but at the same time, you notice, for example, this one, this is on the entire domain. Again, assuming this stops at this point, this is an absolute max, since it is the highest point on the entire domain, and since this is the lowest point on the entire domain, we'll say that this is the absolute minimum. Now, if this point if this graph didn't stop and it continued, then this would no longer be an absolute maximum, and this would no longer be an absolute minimum. Okay, since it continued, it would continue on and on and on. So there would be no absolute extreme values, only local values. But since, in this case, we're assuming that it does stop, we're going to say that this is your absolute minimum. Okay, locally also, because locally it's the lowest point, but we say also it's the absolute minimum. So graphically, that's what it looks like. Now, algebraically, a whole other story. So on this one, what I want you to do is we're going to use the first derivative test to identify local extrema Okay. So the first thing we're going to do is find the derivative. To find your extrema, you need the first derivative. So that gives you negative 6x squared plus 12x. And then you set this equal to 0. Negative 6x squared plus 12x equals 0. Take a negative 6x out. That gives you then x minus 2 quantity. And set it equal to 0. So this set equal to 0 is 0. And x minus 2 set equal to 0 is positive 2. So then those are our critical points. So now there are a lot of different methods to do this. You can look online and find other methods. You know, people use tables or whatever. But I'm a visual learner, so I'm going to use a table, and I'm going to go ahead and put our critical point, or not a table, but a graph. I'm going to go ahead and put our critical points on that graph, and I'm going to label those as red, since they're critical. Now, the first derivative test requires that we use test points to the left and to the right of each critical point. You can choose any value. You can choose negative 100 if you wanted to, but to keep things simple, I'm going to keep negative 1. And I'm going to choose 1, and I'm going to use 3. Again, you could choose any number between 2 and positive infinity, and any number between 0 and negative infinity. It does not matter. Sometimes a bigger number will make it a little more obvious because we're not interested in actual numerical answers here. I'll show you what I mean. So we're going to go ahead and find the first derivative. Keep this in blue. We're going to go ahead and find the first derivative at negative 1. Okay, now you do not use the original function. You use the first derivative at each point, because the first derivative test, all you care about are the slopes, if it's positive or negative to each side of your critical point. So if you plug negative 1 into your derivative function, so it'd be negative 6 times negative 1, then times negative 1 minus 2. Again, all you care about is if it's going to be a positive or negative answer. So this is going to be positive. This is going to be negative. So a positive times a negative, you're going to get a negative answer. Again, plug 1 in there. That's going to be a negative product times a negative product. Gives you a positive product. That's why it doesn't matter if you plug negative 7,000 in here. Negative 6 times negative 7,000 is still going to be positive. But then when you take negative 7,000 minus 2, that's still going to be negative. Again, it doesn't matter. Okay, so in the last one, you take negative 6 times 3. You could plug 300 in there just for kicks and giggles. Let's do that. Then you would have 300 minus 2. And again, this is going to give you a negative product, but this is going to give you a positive sum. So a negative times a positive gives you a negative answer. Now, what this means is to the left of 0, all of our slopes are negative. Between 0 and 2, all of our slopes are positive. Because remember, it can only change from negative, positive, positive, negative at critical points. That's why we only need a single test value to each side. And then to the right of 2, when we plug 300 in there, it went back and had negative values. if we just really quickly sketch what this graph looks like at these points, it looks something like this. It goes from negative to positive, and then at some point here it goes then from positive to negative. All right. Now if we write our answer, we're going to say that there's a local maximum at x equals 2, a local minimum at x equals 0, and then also we're going to go one step further and identify where it's increasing or decreasing. So we would say that it's increasing on the domain from 0 to 2, and it's decreasing on the domain. Going to have two sets. It's going to be from negative infinity to 0, union with, then it goes from 2 to positive infinity. Whoops. That's positive infinity. Ignore that. All right, so then we know when it's increasing and when it's decreasing. And then one last example. I know this is a, where's that example at? Long video, but here's our last example. And on this example, we're going to use the first derivative test to find any critical points. So first of all, you notice here that they already give us our first derivative. So there's no calculus to do. The only thing we have to do is use our first derivative test. And you know our critical points are going to be at 1, 2, and 4. Set each one of these equal to 0. So you're going to have a critical point at 1, you're going to have a critical point at 2, then you're going to have a critical point at 4. So we need test values to the left and to the right. So we're going to have 4 test values. So you're going to test a value at, let's say, 0. Have another test value, so this would be 0. Let's have another test value at 1.5. Whoops. Have another test value at 3. And then have another test value at, let's do 10. Doesn't matter what value you choose as long as it's larger than 4. Then if you plug these values in, when you plug 0 in, you have 3 products. The first product would be positive, the second product would be negative, the third product would be negative, because 0 minus 1, that's a negative, but you're squaring it, so it's going to be positive. 0 minus 2, that's negative. 0 minus 4, that's negative. So positive, negative, negative gives you a positive answer. So then that means on the left side of our first critical point of 1, all going to be positive slopes. When we plug 1.5 in there, again, this is always going to be positive, but then you're, again, going to have negative, negative, giving you another positive answer. So there's some kind of a horizontal tangent there, but it doesn't change slopes, so there's no extreme value at 1. So you have to be really careful with that. Then at 3, this is always going to be positive. 3 minus 2, that's positive. 3 minus 4, that's negative. So you get a negative answer. And then if you plug 10 in there, that's why using really large values of positive or negative might make it a little easier. But when you plug 10 in there, all of them are going to be positive, giving you obviously a positive product. Okay? So then that means there's a horizontal tangent right here, but it's always increasing, so it might look something like that there. Okay, whatever it looks like. But then it goes from positive to negative, and then negative to positive. So our graph is going to look something like this. Later on, when you learn to find the second derivative and use your inflection points, you can get a more exact graph, but for now, this is going to be good enough. That's what our graph looks like. So we're going to go ahead and identify our local max and local min. So where it goes from positive to negative, that is a maximum. So our local maximum occur when x is equal to 2. Local minimum occurred when x is equal to 4. and then that's it. And you notice there's nothing, we can't find the point, like the other coordinate. We can't find the y coordinate because we don't have the original function. And right now, with our knowledge of just derivatives, we don't know how to find the original function. So this is as far as we can do. So here's the key. When you're asked where does such and such occur, you're really only concerned about x. Yeah, if you can find the coordinate on the original function, that's fine. But really, your only concern has to be x, because x tells you where. If you're asked what is the value, something like that, then you're concerned about the y value. Later on, when we apply finding the derivative, optimization problems, finding the first derivative is equal to 0, max, mins, then the y coordinate is really important. Right now we're just learning to find where they occur, and in this case we can't find the y because we don't have the original function. So anyway, we now know how to use the first derivative test to find local max, local mins. That was the goal of this video, and it's a long video, good examples, a lot of stuff, but that was the goal of this, to find local max, mins, what they look like when they occur. And remember, anytime you find the critical point, do not always assume that a local max or local min occurs at that point. There are other things that could happen. You just have to test them.